Hi, my name is Samantha Nelson, and today we're going to be looking at the synthesis of alcohols from aldehydes and ketones. So first we're going to take a look at this hydration reaction. You can see here that we're going to start off with a ketone. It's important to first protonate this ketone, the oxygen on the ketone, in order to make it a strong electrophile. So this positive charge attracts electrons and making this carbon more delta positive, a stronger electrophile, and that is increasing the electron density on the oxygen. And you can see we're leaving this more open to attack from a nucleophile. This pronation of the carbonyl is known as activation of the carbonyl, which allows water, which is a weaker nucleophile, to attack that less electron-dense carbon. Without protonation, there would not be any attack on the carbon in the ketone. So after that protonation, you're going to have a water molecule attached to this diol compound. Another water molecule is going to come in, take that hydrogen, and reproduce our reagent H3O+. This actually creates a diol, which is two alcohols in a compound. This also works for the formation of hemiacetals, which is just it's in ether group and an alcohol group attached to the same carbon. Acetals are similar with two ethers instead of any alcohol groups, but since we're only focusing on alcohol, I'm only going to mention hemiacetals. There's another reaction with the cyanohydrin formation. So you're using a cyanohydrin nucleophile for this reaction. We're going to be working with an aldehyde. So this is a strong nucleophile, so it's just going to readily attack that carbon electrophile on the aldehyde. It's going to open up and create this negative oxygen, and after protonation, you're going to have an alcohol and a cyano group on your molecule. Next is used as oxidation. Oxidation is not my first choice when going from an aldehyde or ketone to make an alcohol. The alcohol group is formed in a carboxylic acid, which is a byproduct of the oxidation. So if your main focus is to produce the alcohol, I would not use an oxidation, but just for learning purposes. We're going to be starting off with a ketone, and the reagent we're going to be using is MCPBA. So in this short example right here, we're using peroxy acid, but this is MCPBA is known as a peroxy acid. Other reagents that you could be using is KMNO4 or AgO2 in NaOH solution. So in this mechanism, you can see that the oxygen is going to be, again, more electron dense, leaving that carbon to be electronegative. So it's going to allow this oxygen, which is more electron dense, to attack that carbon. And then the oxygen is going to open up and create a negative charge. Due to the attacking of this oxygen, this is going to be a protonated form of the oxygen. Proton transfer is going to occur in order to stabilize that oxygen. After that, there's going to be a transfer of electrons. So these electrons are going to come down and form that double bond again. This R group is going to attack the oxygen, allowing the split of the molecule. So an ester is formed, as well as this carboxylic acid, which we can see the alcohol group is present, but again, it is a byproduct, so I would not use this as your first choice. Another way you could do oxidation is through using chromium reagent. in an acidic solution. So here we're going to use an aldehyde. Again, so the formation of the hydrate or diol shown above here, and then that reacts with the chromium reagent. So the oxygen is going to attack the chromium, open up on this oxygen. There's going to be a proton transfer in order to help stabilize this. And in order to, again, stabilize the chromium, we're going to have a water reagent come on in, steal this hydrogen, and then this bond on the hydrogen is going to form the double bond on the oxygen. In order to stabilize the oxygen, instead of it having 3 bonds, we're going to transfer these electrons to the chromium, which creates your carboxylic acid and a more stable form of the chromium reagent. Again, I would not use oxidation for if you were to do this in like a real world application, but so we're going to go over other ways to make an alcohol. My personal favorites, like go-to, is going to be the use of Greenyard reagents. They're pretty simple to use, and it's pretty simple to use, and it's pretty easy to get the hang of. So we're going to start off, this is a ketone, and by attacking with an MgBr compound, C6H5, you can open up this oxygen, and then H0 plus is used for protonation. So that's how we can get an alcohol. You can go a little further with this reaction, as you can see here. It's what I've started to do by oxidation, just by opening it up, and then you can form your carboxylic acid with another alcohol compound on it. But that's a little more complex than just our regular alcohol synthesis. Next is reduction. I think this is the most popular way to go from a ketone or aldehyde to an alcohol. The mechanism isn't very straightforward, but as long as you know the reagents that you're working with, you'll have a good concept of what the ending product will look like. So in this first reaction, we're going to take a look at lithium aluminum hydride and its use as a reducing agent in solvent THF in cold conditions. So here we're going to be using an aldehyde, and this one's a little more strange considering that the equivalence is going to be a little off. So we're using 4 of the aldehyde molecules per 1 of the aluminum hydride molecules. So the bond between hydrogen and the aluminum hydride is going to attack the carbonyl. This is going to open up the oxygen and create this sort of ion that is going to be associated with the aluminum hydride. You can see here it sort of looks something like this. This reaction will actually happen 3 more times in order to stabilize the aluminum. And leave that on there so you guys can see where we started from. And then in order to, again, continue with this reaction, you're going to have an alcohol reagent, an attack on a water molecule reagent, and that's going to open up on the oxygen, and you can see that this is going to protonate the alcohol here. So it would technically be this oxygen bonded to the hydrogen, as we see here. Another reagent you could use for this reduction reaction is sodium borohydride, NaBH4. The reaction mechanism is very similar, except it's with borohydride instead of aluminum hydride. Personally, I don't have a preference on which one I would use. So we're going to be using an aldehyde in this situation. So again, we're going to have the bond between the hydride and boron attack the carbonyl. It's going to open up on the oxygen. This arrow, in case you didn't pick up on it, it means associated with. So it's not directly bonded to just yet, but it is associated to that ion, basically. You can see here is that this is the starting molecule that we will go off of. In order to stabilize this oxygen, it bonded to the boron. This reaction, similar to the aluminum hydride, happens 3 more times to make this boron complex. In order to stabilize that, since it has 4 bonds, water is going to come in, protonate the oxygen so it breaks the bond here. And you can see through that it creates the alcohol in the compound. Some cool things about sodium borohydride is that you can actually use it to add deuterium to your molecule, depending on where your deuterium is located in your process. So if you use the deuterium, boron deuterium, instead of boron hydride, your deuterium is actually going to end up attached to your central carbon here. And that's shown through this mechanism where the boron with all the deuteriums attached are going to attack the carbonyl. It's going to open up, and then through protonation, which H3O plus in the second step, you're going to get that alcohol. But however, if you leave the sodium borohydride alone and if you work with D2O, so 2 deuterium and 1 oxygen instead of H3O plus, you're going to add your hydrogens to that central carbon as usual. However, your oxygen is going to be protonated with the deuterium instead. So that's interesting to look at if you wanted to just compare the use between hydrogen and deuterium, which actually we do tend to use almost interchangeably in this class. Lastly, looks a little bit about Nichols reagent in reaction in class. However, we didn't go over the mechanism due to its complexity. But what I would note about this is that nickel bonded to 2 hydrogens can be used to reduce the ketone to an alcohol, as well as reduce an alkene to an alkane, which could be helpful if you're trying to eliminate the use of a multi-step reaction and just do it all in one go. So this was just a general overview on the synthesis of alcohol from aldehydes and ketones. Again, you can use the hydration reaction, a cyanohydrin formation, oxidation, Grignard, or the general reduction of a carbonyl to form that alcohol.